This is the nephron of the kidney, and you can see this is the Bowman's capsule holding the glomerulus in it, and here the blood vessels are inside, and what they have got, they have the osmolarity of almost 290 to 300 milliosmol per liter. So for easy understanding, we consider it at just 300. Now, this osmolarity at vascular pole, right? This is the vascular pole, is the same as that on the urinary pole because the fluid that is moving in this proximal convoluted tubule, we call it as ultrafiltrate, up to its convoluted part and rather its straightened part has got 300 milliosmol per liter, right? Now what happens, we consider here the thing that the osmolarity is supposed to be increased downwards. As you can see, it has to become 600, then 800, and if you consider, it has to be 1200 at the base. The medullary interstitium has to be hyperosmolar. As you can see that it is increasing down from 300 to 600. If you can notice, then 800, 1000, and of course 1200. And this is basically due to the fact that if you reconsider that this descending limb is permeable to water, and the water is going outside in the interstitium, or we can say it is being resorbed here, so causing the ultrafiltrate inside to be hyperosmolar, right? And when it has to move upwards, what is going to happen? This ascending limb is permeable to solutes. Now, what we can expect, that this interstitium is getting its hyperosmolarity due to the reason that this ascending limb is permeable to the solutes, right? And the ultrafiltrate that is now moving upwards is now towards the hypotonicity, right? It is up to reaching at 400 at the very start of distal segment, right? As it ascends upwards and passes through distal convoluted tubule, it becomes near to that of 50 to 100, right? Now we can say that as it comes downwards into the collecting duct, its osmolarity should be changed in a sense that the distal convoluted tubule and the collecting tubule, they are under the influence of ADH, which is vasopressin. Now, as you can see, this is the distal convoluted tubule, and finally it is going to enter into the collecting tubules. Okay, these both, they are sensitive to ADH, right? Antidiuretic hormone or vasopressin. Okay, this vasopressin, if you can recall, let me draw something for you, that if you can see, this is the hypothalamus. It has got osmoreceptors. They sense this osmolarity change, and there is a nucleus which is called as supraoptic, and this supraoptic nucleus is supposed to secrete vasopressin or ADH, right? And causes water retention, or water should be reabsorbed like this. Okay, and we have got so many aquaporin proteins channels that allows the passage of water into the interstitium. And now our ultrafiltrate that has to become concentrated urine, its osmolarity is keep on increasing from 400 to 800. You can see it, then 1000, and almost when it reaches towards the tip of the collecting duct, right, it gets up to the level of 1200 milliosmol, right? And of course, this whole system that is showing the downward passage of the fluid and the upward ascent, so they all causes the countercurrent multiplication of this whole kidney medulla interstitium that becomes hypertonic, right? And what else contributes to this countercurrent mechanism is the urea, right? this urea, which acts as a solute, also helps out or maintain this countercurrent multiplication, right? This segment, the loop of Henle, and this up to the collecting duct in the cortex, this is less permeable to the or least permeable to the urea. But when we enter into the medulla, this collecting ducts, they are very much permeable to urea, and it gets in the interstitium of the medulla to become hypertonic, right? Okay, in this way, now we know that the permeability of this urea that causes hypertonicity in the medulla or its interstitium, right? And it plays a significant role by its recycling because it gets again resorbed in this interstitium and causing its hyperosmolarity, right? So there is another thing in addition to this loop of Henle and the role of urea and the ADH, right? So these three things, they are rather taking part in the maintenance and in the exchange. And of course, the loop of Henle is the basic component that causes the multiplication in the countercurrent mechanism. We see the flow in the countercurrent way in this loop of Henle with the help of it, right? The vasa recta, as you can see, has got the descending part and the ascending part, right? And they also contribute in the exchange and maintenance of the countercurrent mechanism. Though it's a slower process or the flow is not very much high, but you can see that as the water is supposed to get in or being absorbed, and on the ascending side of the vasa recta, it is reabsorbed in the interstitium, right? And the solutes are also in the same manner has to follow. And another important thing, as you can see, that if I mark this lighter portion of the nephron is supposed to show you the higher water permeability on the descending limb. Then you can concentrate with the turquoise color. This is the ascending limb of loop of Henle, showing the total impermeability of water along with this ascending limb. And then finally, you observe that this distal convoluted tubule and the collecting tubule, under the influence of ADH, they allow the permeability of water, right? This is how this countercurrent mechanism works. Most of the sodium has been resorbed in this proximal convoluted tubule, right? And rest of which is just left could be absorbed by the distal convoluted tubule, right? And they all are trying to conserve the sodium. And in addition to it, they causes the urine to be passed as hyperosmotic. This is the point we should note. If we concentrate on the vasa recta, we can see it has got a descending portion as that of the loop of Henle and the ascending one, right? So you can see the passageway of water that is being reabsorbed in the medulla interstitium, right? And finally, what is also happening that the electrolytes or solutes, you can see from the ascending portion of the vasa recta, they are trying to enter into the interstitium. So in simpler term, the water from the descending portion of the vasa recta is entering into the medullary interstitium, keeping it hypertonic and then being absorbed by the ascending portion of the vasa recta. And in reverse, the things happening that the solutes, they are from the ascending vasa recta are entering into the interstitium and then into this descending portion, right? So the countercurrent exchange multiplier system includes, what do you see here is the first we have got 300 milliosmol concentration of solutes in the blood, and when it has to become ultrafiltrate in the proximal convoluted tubule, the same level is maintained, and finally it has to be increased downwards up to the 1200 milliosmol per liter, right? And in the same way, the interstitium of the medulla has got the hypertonicity up to 1200 milliosmol, and this is all contributed by the vasa recta, and you can see the main element is the loop of Henle. You can see this descending nib is showing the reabsorption of water in the interstitium.